Good morning, everyone. I'm Chetan Deshmukh, and the topic of my talk today will be some work towards non-destructive detection of photonic qubits that we did at the University of Calgary. I'll first go through our proposal for doing such a non-destructive measurement, which was mainly worked on by the group of Christoph Simon at the University of Calgary, along with Kabat. And the experiment, the proof of principle experiment, was conducted in Wolfgang Tittle's lab along with Neil and Daniel. So to first start off with what a non-destructive measurement is, it is essentially a measurement that preserves both the particle as well as its state. So you perturb the system in such a way so as to not disturb the variables that are of interest to you. So if you consider a signal on which you want to do your non-destructive measurement, you undergo this measurement and end up obtaining both the particle at the end of the measurement as well as the state in whatever state was encoded into it. So there are different kinds of non-destructive measurements you can do, and the particular one we are interested in is doing a number non-destructive measurement where we try to detect the number of photons present in such a signal. So the reason we are interested in such a measurement is mainly because of the applications it has in building quantum networks. If you try to take the particular example of a quantum repeater where you have sources of entangled pairs at the nodes, where one pair is stored in a quantum memory while the other pair is going towards a Bell state measurement station for entanglement swapping. Many of the times what happens is that the photons that travel towards the Bell state measurement end up getting lost. So here you use quantum memories to synchronize this process of Bell state measurement. So if you end up losing one of these photons, when you actually conduct your Bell state measurement, it won't be successful and you end up losing that trial. So what you could do if you had such a number measuring device was that you could do each of these number measuring non-destructive measurement at the nodes, at the Bell state measurement node, and only go ahead with this Bell state measurement if you actually have a photon at that node. So this would definitely improve the efficiency of your entanglement swapping. Another more specific example would be to improve the performance of single photon sources based on spontaneous parametric down conversion. So what happens in such sources is that you pump a nonlinear crystal with strong laser light, and it produces a pair of photon with certain probability, but it also has a certain probability of producing multi-pair photons, so 2 or 3 pairs of photons, which are not desirable. So measurement like a number measuring device like this, which preserves the photons, would help you getting rid of all the events where you ended up producing more than a pair of photons. So most of the current approaches to doing such a non-destructive measurement of photons involve making this signal that you want to do the measurement on, making it interact with another probe another pulse that we call as the probe photon via some medium, and this interaction somehow tells you some information about the signal. So you don't end up measuring the signal itself, but some measurement on the probe tells you the number of photons that you had in your signal. So as you might expect, this involves getting a really strong interaction between the two photons. So there are currently many systems being pursued in getting this strong interaction. So one of the most successful ones is coupling single atoms to high finesse cavities, which is mainly being pursued by Rempe's group at Max Planck. And so all of these involve an atom with a really strong coupling to light and different kind of atomic systems. Along with single atoms, people are also pursuing coupling atomic ensembles, which are also coupled to high finesse cavities, where the interactions are mediated by either Rydberg blockade or by AC Stark shifts. So while these have demonstrated really strong interactions, there hasn't yet been a proposal of implementing such measurements in a solid state environment. It would be really interesting to investigate what happens in solid state, because they are generally considered to be more practical, where you can easily integrate them on chip, and also if you can somehow integrate it with other solid state components that we already have for quantum photonics, that would be good for the community. So that's what we are trying to do. We will essentially use rare earth ions doped into crystals, which in our case is a thulium doped into a lithium niobate waveguide crystal for mediating this interaction. So the way we go about is that we store this probe pulse that we will use to mediate the interaction between the signal and the probe. And while this probe is stored, we pass our signal through our crystal, and this induces some interaction between these two. And while the signal goes undetected, we detect the probe and extract the number of photons in our signal. So before I go on discussing exactly how we do this and how we implement, I'll just briefly talk about the storage protocol we use for our probe. It is a protocol called the atomic frequency comb protocol. So what happens in such rare earths doped in crystals is that because of local field effects, these have a huge inhomogeneous broadening, which means that they absorb over a huge frequency range. So we start off by tailoring this frequency, this absorption profile into these periodic structures that you see here, frequency separated by delta m. So this sets a predetermined storage time given by 1 over delta m. So we have our probe that will be stored in such an AFC for 1 over delta m time. So this is how it looks. Our proposal looks first in frequency, where you have our pre-programmed AFC, where our probe will be stored. And you can see how it will work in time. You start off at a certain time by storing the probe, and while the probe is stored, you send your signal through your medium, and the interaction that we use in this system is an AC stark shift. So while the probe is still stored, we pass the signal, which essentially passes through a transparency window with hardly any absorption. So once the signal passes through, we then recollect the probe, and there is the AC stark shift that the signal induces on these atoms is imprinted on the probe in the form of a phase shift. And we detect this phase shift, and we see that the phase shift that we extract onto the probe depends linearly on the number of photons in your signal, and also certain other experimental parameters, such as the spontaneous decay rate of our atoms, and inversely on the cross-sectional area of interaction, as well as the detuning of the signal. So that is the phase shift that is imprinted on the probe, and we extract this phase by doing a homodyne measurement of the recalled probe with a local oscillator. So that is what our setup looks like, where we have a 795 laser, which is resonant with the thulium ions, which frequency and intensity modulates our laser. So what we create using this laser is the structure that you just saw, where you have an atomic frequency comb at the center, surrounded by almost transparent bins through which the signal can pass through without getting really absorbed. So we do this by a technique in quantum optics called optical pumping, where you pump out the ions that you do not need into a shelving level, which has a really long lifetime. So you end up creating this kind of a structure. So in time, this looks something like this, where you have a certain time for which you create your spectral structure like that. You wait a certain time and actually conduct your experiment, and you extract your phase by doing a homodyne measurement, and then followed by a repeat cycle where you again start back at the start. So the first step would be to see if you get the phase shift that you need. So that we do by, in the first case, we pick a certain detuning for the signal, and by keeping every other parameter in the formula the same, we vary the number of signals linearly. And we expect that the phase shift should go up linearly, and that is what we see in this inset over here, where for a particular detuning of the signal, the phase shift is linearly going up. So I should mention here that all of this proof of principle was done with really strong light. So you can see that the number of photons that we used in our signal are of the order of 10 to the power 8. So that's quite 10 to the power 6. So that's quite high, but we get the phase shift that we expect. So now that we know that the experiment is working, we try to see if such a phase shift measurement based on the signal, is it somehow doing anything to the signal? So for that, we send our signal and encode it in time bins and see if that is inducing any extra errors in our signal. So what you see here is the, so first of all, to talk not about the inset, but the main figure, you see the phase shift when we actually send in the signal versus the case where we do not send in the signal. So the green case is where you do not have this non-destructive measurement and you do not see any phase shift, which is what you expect. And when you instead send in your signal in whatever different kind of time in qubit states, you end up getting exactly the same phase shift for each of them. So the phase shift is, does not depend on your qubit state, which is what you want. Now, does this kind of an interaction induce any errors? As we see from the inset over here, in the inset, the green, we are plotting basically the error rates for different time in qubit states that we send in. For the green, these are the erroneous rates that are induced onto the signal without our non-destructive measurement happening. So there are a certain amount where we are mainly limited by the interferometric visibility that we have. So the red ones are the error rates that we induce if we are actually doing the non-destructive measurement. So we see that we don't really induce any extra errors onto a signal, except for one case, which is if you send in your signal as an early time bin. So the main reason for that is that the signal, as it goes through your crystal, there are still a few atoms that are actually present, which will somehow end up attenuating the signal, so they go into the excited state, and they have this free induction decay, which comes out at a later time after your signal passes through. So all the signal that actually you send it in an early time bin ends up coming a little bit into the late bin. So that can be improved with more efficient optical bumping, basically. So obviously, the phase shifts that we saw were quite small to be done with just single photons as your signal states. So to actually go and improve this phase shift, where you can detect just single photons, you need to scale up this phase shift at least by a few orders of magnitude. So one way to do that is if you look just at the phase shift, which depends linearly on the decay rate of the atom and inversely on the cross-sectional area and the detuning, you can first of all reduce the interaction cross-sectional area, which means that instead of using the waveguide that we currently used, which has a mode diameter of roughly 10 microns, you can in principle go up to a micron, which is dictated by the wavelength. So you end up gaining a few factors over there. So the other things you can do is make your signal such that it is much less detuned from your probe, which induces a higher and higher phase shift. But one thing you have to be careful is that if you increase or decrease your detuning to get a higher phase shift, you end up losing more and more of your signal because it gets off-resonantly absorbed by your atoms. So one way to do that is to not reduce your detuning, but to keep it constant, but just pass your signal multiple times. So that ends up giving you m times higher phase shift if you pass the signal m times. And by keeping the gamma over delta ratio small enough, you can end up with a smaller signal loss, but the same phase shift. So we can also get a similar analogous effect if you use a cavity instead of a multipass, which we are still in the process of investigating. So I think that's all I had. With that, I'd like to thank all my people who made this work possible, as well as all the funding agencies for giving us funds. Thank you.
So, time for a couple of questions. I'll start with one. So I'm going to a multiple pass, a recycling configuration is the same as having a very long waveguide, right?
Yeah, it would be.
Pardon? We can't hear you. Sorry, the question is, if you have going a multiple pass, multiple recycling scheme is equivalent to going through a very long waveguide.
Yes.
And so the phase shift is linear with the length of the waveguide, and the loss is also linear. So why does that actually help?
So yeah, so what you can do instead of just keeping it longer is that the phase shift depends linearly, or if you consider the gamma over delta as a parameter, the phase shift is just linearly dependent, while the loss is quadratic over that. So you can just make your gamma or delta parameter smaller and smaller to get a smaller loss, but your phase shift, you can compensate for that by a larger pass.
Then how long would you need, what length can you estimate you need to go with your current level in order to,
yeah, so
how many cycles?
So one thing we tried to estimate was with a waveguide that is of the order of the wavelengths, we would need roughly 1,000 passes to achieve a phase shift that can be detected using the current detectors. So you need essentially really low loss switches.
Other questions? Okay, now let's thank the speaker again.